Okay, we'll start out our journey into heat transfer first by taking a look at what's called the mechanical equivalent of heat. This is a very long and tortured phrase that has a lot of history behind it. In the early days of thermodynamics, people understood that, say, when you lit a flame underneath a beaker of water, so if you stuck a thermometer in a beaker of water, you'd see that the temperature would go up. And with enough work, they understood that something was being transferred between the flame and the beaker of water, but they didn't know what. They knew that this something was being conserved, and so they started taking a look at heat flows and keeping track of how all the heat was going in and out. But it took quite a while longer for people to realize that these heat transfers were really causing exchanges of thermal energy, the random motion associated with individual atoms and molecules. And so it wasn't known for quite a while that these were actually energy transfers. As a result, we have some legacy units dating back to when the physics community didn't know what was being transferred. What tied this together is an experiment due to Joule, yes, as in the person who eventually became the unit. He did an experiment where instead of using a beaker of water and lighting a flame, he stuck basically a paddle wheel inside a beaker of water and ran a collection of pulleys to have a falling weight spin the paddles wheels around. And he saw that when that was happening, that the temperature of the water also went up. So for a while, the physics community said, well, okay, apparently if you do mechanical work on a fluid, you can also cause its temperature to raise. But they weren't quite immediately willing to make the jump that heat was an energy transfer, which we now know it is. Thus, the very convoluted phrase, the mechanical equivalent of heat, where we're saying if you do a certain amount of work, you will achieve the same effect as if you had a heat transfer from the flame, which again, like I say, we now know that these are all energy transfers, but the convoluted terminology still exists. So the equivalency is 1 calorie. A calorie is the heat required to raise 1 gram of water 1 Celsius degree, or 1 Kelvin, since they're the same thing. And it turns out that if you do direct mechanical work on the water, like with this paddle wheel contraption, you need to do 4.184 joules. So we now recognize that the calorie is indeed a unit of energy and that it is equal to 4.184 joules. Now, a couple of quick notes on this. In the United States, if you look at, say, your candy bar wrapper or something like that, okay, you look in the nutrition facts panel, they'll say calories, but they always write it with a capital C. And annoyingly, this calorie is 1,000 of the other calorie. This is called a great calorie or a food calorie. So capital C is 1,000 of lowercase c calories. This is often written as kcal in order to help avoid the confusion. In other nations, in their nutrition facts labeling, they'll often write explicitly kcal to avoid this confusion, or some countries like Australia actually quote all their food energies in joules. In fact, you can look at a can of Diet Coke in Australia and it says low joule cola, which is awesome. So anyway, so that's the starting point there. We know that heat transfers are transfers of internal energy, and 1 calorie is 4,184 joules. Again, if you've had some sort of background in general chemistry, you're probably used to working in calories. And again, the physics community is more apt to be working in joules. So that, again, will mean a lot of numbers that you're used to will be different. Okay, so with that, let's start to think about phases before we think about phase transitions. I'll ignore plasma for now, and I'll just instead look at solids, liquids, and gases. So remember, in a solid, the solid has a definite shape. Definite, that's a really bad H, and a definite volume. So you can go and stick an ice cube in a glass, and the ice cube will just sit there. On the other hand, a liquid will have an indefinite shape, but a definite volume. So if you pour some water into a glass, it will assume the shape of the glass, but the volume occupied by the water won't change. A gas is hallmarked by having both an indefinite shape and an indefinite volume. In other words, gases will always expand to fill the container that they're in. On an atomic or molecular level, what this looks like is for a solid, you typically will have all of your atoms arranged in some sort of a lattice, held together by intermolecular bonds, like so. In a liquid, there will still be some attraction between them. And so what you'll see is the spacing really isn't usually too terribly different than you would have in a solid. But now the atoms are free to move around, and you'll see them like swap places with each other. So that's the big difference between a liquid and a solid. With a gas, on the other hand, there isn't even this attraction anymore that's keeping the atoms near each other. They're all just flying off in random directions, doing their own thing, and mostly interacting with the walls of the container. Now, depending on the situation, if we're adding energy to a solid, what will happen is eventually these bonds will get longer and longer and longer as the atoms are vibrating more and more aggressively, until it becomes energetically favorable to break these bonds, and you'll transition from a solid to a liquid. That gets called melting. And similarly here, if you add enough energy to the liquid, you'll eventually get to the point where the molecules are so agitated that this weaker form of intermolecular attraction is no longer enough, and eventually becomes energetically favorable for this level of bonding to rip apart, and this will get called boiling. If you go in the reverse direction, so say if you take heat out of a gas, so if you transfer thermal energy out, the atoms start moving slower and slower and slower, and eventually when they start to interact with each other, they'll want to hang out with each other. This would be condensation. And as that process continues here, eventually the atoms won't want to swap spaces with each other anymore. They'll want to have a more rigorous bond structure that forces them into a lattice. That gets called freezing. Now, it is possible to shortcut the liquid stage. Depending on the pressure, you may not necessarily go through the liquid phase. For instance, dry ice is solid carbon dioxide, which at atmospheric pressure, it is just energetically favorable for it to go straight from solid to gas without going through an intermediate liquid phase. That process gets called sublimation. And the reverse process, if you transfer enough heat out of the gas, transfer enough heat out of the gas to make a solid directly, that gets called deposition. Okay. But the main deal here is that there will, in any of these processes, there will be heat associated with either forming or breaking bonds. So to characterize this, we'll start to introduce a heat flow diagram. And so at the moment, I'm just going to imagine something like I've got a block of aluminum right here, and I'm transferring heat in. One of the standard ways that people will note that is, here's my substance. A double line with a little arrowhead indicates some sort of an energy transfer in and out. And if it's a heat transfer, the symbol for heat is Q. Okay. Now, if we want to characterize how the temperature changes, we know that heat is an energy transfer in or out of a substance. So if we're transferring heat in, what's going to happen is you're going to make the individual atoms and molecules move around more violently, and also on average increase the average bond length, which will increase the potential energy of the bonds. All of this will have the effect of increasing the average kinetic energy of the atoms in question, and also the effect of increasing the thermal energy. And if the thermal energy goes up, by definition of temperature, that means the temperature goes up. So what's going to affect that? Well, we're going to transfer in so much heat, and as a result, we're going to get a change in temperature. The two things that can affect that are going to be the mass of my substance, which is a proxy for the number of atoms, but it's much easier to measure a mass. But really, it's the number of atoms involved. If I have more atoms that I have to get moving more violently, I'm going to have to transfer in more energy to have the same amount of thermal energy, of average kinetic energy per molecule. And then the rest of it's going to depend on details of the structure of the atom, the bonding, etc. We lump all of that into what gets called the specific heat, or more technically, the specific heat capacity. To make the units work, they'll have units of joules per kilogram Kelvin. So this is telling us how much energy we're going to have to transfer in to raise 1 kilogram of the substance by 1 Kelvin. Now you've probably, if you've had general chemistry before, you've probably seen these in units of calories per gram degree instead of joules per kilogram degree. So you're going to see a lot of things differ by a factor of 4,186 as a result. But let's just do a quick example of that. So I'm imagining that this is a block of aluminum. To make this concrete, let's say I transferred 1,000 joules in and that the mass was 2 kilograms. If we say the initial temperature was 15 degrees C, you can ask what is the final temperature. Okay, so we'll start with the heat transfer is equal to the mass times the specific heat times delta T. And delta T is going to be the final temperature, which is what we want, minus the initial temperature, which is what we have. Now, an important thing to note here is that, remember, a C degree and a Kelvin are the same thing. So if your temperatures are in Celsius, in a situation like this where you have a temperature difference, there's no need to convert to Kelvin. However, there will be times in thermodynamics where you will need to convert to Kelvin. So, general rule of thumb, if the relation has differences, there's no need because all you'll be doing is adding 273 to each number and it's all going to cancel out. But if you're ever unsure, it's never a mistake to convert to Kelvin and then convert back out at the end. It just might be some needless extra steps. All right, so with that out of the way, we can do a quick bit of algebra. T final minus T initial equals Q over MC. And so T final equals T initial plus Q over MC. All right. Now, I know that because this was a difference here, we can leave this in Celsius, so that's what I'm going to do. I'm going to say 15 degrees Celsius. The heat transfer we said was 1,000 joules over 2 kilograms. And if you look it up in the tables, the specific heat of aluminum is usually quoted as about 900 joules per kilogram Kelvin. All right, so this will be kelvins at the end once you cancel all the units and everything. But remember, kelvins are the same thing as C degrees, so I have compatible units. And when I punch it through, I will get 15.6 degrees C. Again, if you're ever unsure about whether you should leave it in Celsius or go to Kelvin, it's never a mistake to go to Kelvin. It's just at the end you may find yourself needing to subtract 273 when you didn't need to. All right. Now let's think about what happens instead when you're changing a phase. So when you have a phase change, let's look at melting as an example. So I've got myself a glass of water, and I'm floating an ice cube in that glass of water. And let's just say I go ahead and I start running a Bunsen burner underneath it. So we're transferring heat into the system. Now, the ice cube and the liquid water are in thermal equilibrium with each other. The average kinetic energy of the molecules will stay the same. However, if you're in equilibrium at STP, then the temperature is 0 degrees C. However, what will happen is the heat goes in. At this particular point, as we're continuing to add thermal energy into the system, the most energetically favorable thing to do is to do work to break bonds for the molecules on the surface and cause them um, to break those bonds and then float in with the rest of the liquid water. This doesn't change the average kinetic energy of the molecule. We're just doing work against the bond. So as a result, the temperature doesn't change. But you had to transfer a lot of heat in to make that happen. Another example of this, maybe to help think about that, is if you've ever flown into an airport and you're coming in for a landing and the pilot wound up having to fly you through a cloud on the way down. You may have noticed that you had yourself a very bumpy ride. And the reason you're having a bumpy ride is that when you're forming the cloud, water is condensing. So as you're forming the bonds between the adjacent water molecules to make the water droplets, you are releasing heat out into the environment. So you wind up having a net heat transfer out. This heat transfer winds up causing turbulence in the air. In fact, some kinds of clouds can be so turbulent, and they're actually the ones that often look light and fluffy and not terribly dangerous to us on the surface of the Earth. Some clouds can be so turbulent that you could run a real risk of doing structural damage to the aircraft, which that usually doesn't end well. So pilots tend to be very concerned, even when they're flying on instruments, about trying to fly around as many clouds as they can. However, there are certain kinds of clouds that they can fly through, and so a lot of times on landing they're flying through the clouds in order to maintain good traffic flows in the area. So we're going to have a heat transfer in or a heat transfer out. In either case, the temperature isn't changing because we're not changing the average kinetic energy of the molecule, but we are either breaking bonds in the case of melting the ice cube or forming bonds in the case of condensing the water droplets. And so to break bonds will require the transfer of heat in. When you're forming bonds, because that's a lower energy state, you'll end up having a heat transfer out. Now, when we have a heat transfer out, because physicists consider heat transfers from the perspective of always being on the system, this would be a positive heat transfer, and since here our system's the cloud, that would be a negative heat transfer, because we're effectively, if heat is being transferred out of the cloud, that's the same difference as adding negative heat into the cloud mathematically. Okay, so to account for how much heat is required to either to break bonds or how much heat you get transferred out when you form bonds, physicists keep track of a quantity called the latent heat of the substance. In chemistry, this usually gets the name enthalpy of formation. For historic reasons, the names in the different fields evolved differently. So here, the heat, if you are, let's say, melting or freezing something, this will be plus or minus the mass of the thing, because again, that's a proxy for counting how many bonds we're talking about here, times what's called the latent heat of fusion. Of the substance. That's if you are melting or freezing. If you are boiling or condensing, it looks just the same, except we call it, L sub V, and that stands for latent heat of fusion. And this stands for latent heat of vaporization. And this is if you're boiling or condensing. So again, for our units here, to make the units work, I need to get joules out, and all I have here are kilograms to cancel against, so it's joules per kilogram. And again, if you're used to seeing this in calories per gram, you're again going to see factors of 4,186 showing up. So we'll end this one up by doing an example of what's called calorimetry. Where we will take a look at the heat exchanges within a system. So here I'm going to imagine a situation where we've got a beaker of water here. Let's say that this beaker of water, we have 0.09 kilograms of water, and we'll say it's at 80 degrees C. And to that, I am going to add in an ice cube. And this ice cube will be 0.010 kilograms. And we'll, to make it simple, we'll say it's at 0 degrees C. So what we would eventually, what's going to happen is first the ice cube is going to go in, and it's going to melt, and we'll create water that is at 0 degrees C, but then we're still going to continue to have a heat transfer between the liquid water and the freshly melted water until everybody gets to the same temperature. So my strategy for this is to start with a heat transfer diagram. And so this will be the liquid water we have initially, and this will be the solid water we have initially. And we're going to transfer the heat in like so. And I am going to make the whole thing my system. And since the system is isolated, what I can do is I can say the total heat transferred into the system is 0. But I can write this as this 0 as the sum of the heat transferred into the liquid plus the heat transferred into the solid. And yes, we know it's an outbound flow from the liquid, and so it'll end up being a negative number, but the math of the situation will take care of those numbers automatically. So let's go and take a look at this. So we can say 0 equals, so for the heat transferred into the liquid, there's no change in phase at all that we have to worry about. So we can just say, okay, we had water that started at some high temperature. So let's go and call that temperature T liquid initial. And we'll call this temperature T solid initial, just to keep them straight. And then eventually we're going to end up at some final temperature after everything's melted and mixed. So we can write this as the mass of the liquid times the specific heat of water times the change in the temperature of the liquid. Sorry about that. There we go. And then for the solid, we can write a similar expression. We need to write two expressions. One, we have to take into account that since we're at the ice point for the solid, we're not going to be changing the temperature until after we melt everything. So this is going to be the mass of the solid times the latent heat of fusion. And it's going to be a plus sign because it's an inbound transfer. And then we just write mass of solid, specific heat of the water times the changing temperature of the solid. Now here, the specific heat we're going to use is going to be for the liquid phase. Just like over here. And the reason for this is this took care of us going from solid to liquid. Now, if the initial temperature were below 0 degrees C, we would have to have another term like this, where we had the specific heat of the solid phase of water, and we would have to have a temperature change up to 0 degrees C. So that's how you would handle that if the initial temperature were non-zero. Okay. So with these terms here, as we'll see in just a second, the signs take care of themselves with the specific heat. But with the latent heats, you do have to keep track of your plus and minus signs. All right, so now let's go and put these in. So mass of liquid, specific heat. This is going to be T final, which is a mutual temperature, minus the initial temperature of the liquid, plus mass of solid LF, plus mass of the solid C. And then this is going to be T final minus 0 degrees C. And I'm putting in 0 right away because that's always okay. And again, I can get away with doing this because all my temperatures in here are differences. And so we don't have to add 273 to everything. But if you're unsure, then just leave this as T initial and put in 273. That's fine. In fact, let's leave it as T solid initial just to show that it won't matter. All right. Unfortunately, this is just going to be a giant pile of algebra, and there's not a lot we can do about that. So we're going to have to expand all the terms out just so we can try to isolate the T finals. And then hopefully we can do a little bit of grouping back together at the end. So MLCT final minus MLCTLI plus MSLF plus MSCTF minus MSCTSI. All right. Now, what we can do is we can group terms that have TFs in them. So we will have ML plus MS CTF, combining these two terms. And that's something anyway. Plus MSLF. Then we'll have minus for both of these terms. There's a C in common, and that's it. MLTLI plus MS, whoops, plus MSTSI. All right, now we can at least put the TF on one side of the equation, everything else to the other. We're just doing algebra at this point. So ML plus MSCTF will equal, putting this to the other side, the equal sign will make these terms positive. So we'll have C times MLTLI plus MSTSI. And then putting this to the other side will make it negative minus MSLF. All right, and then finally we can divide through by everything. So we will get that T final will equal C ML TLI plus MS TSI over C ML plus MS minus MSLF over the same thing. I broke these apart just so that at least here I could cancel specific heats and make this suck a little less badly. But that's about all we can do with it. All right, and then here we go. Now it's just putting in numbers. So we'll get T final equals, we said that the mass of the liquid was 0.09 kilograms, and the initial temperature of the liquid was 80 degrees C. All right, then plus the mass of the solid was 0.01 kilograms times 0 degrees C. And again, if you want to convert it all to Kelvin, that's fine. At least makes this term 0, so that's something. This will be over 0.09 kilograms plus 0.01 kilograms. Now, to all of that, we've got this term over here. We'll have to subtract the mass of the solid, 0.01 kilograms, times the latent heat of fusion for water, which is 333,000 joules per kilogram. And we will be dividing by the specific heat of water, which is 4,186 joules per kilogram Kelvin times 0.09 kilograms plus 0.01 kilograms. Whew, that is a lot. Anyway, when you grind it all through, you get 64 degrees C, which is something to be happy about. When you get done with these kind of problems, you jolly well better have the final temperature in between the two initial temperatures you had. If you find yourself, say, ending up with a negative temperature or something like, a temperature that went below the cold initial temperature as an example, then what that probably means is that there's actually a phase change that either you didn't take into account, or it'll turn out that you won't complete the phase change and you end up at the equilibrium temperature. So those are edge cases that you have to watch out for. All right, in the next video, we will take a look at some more heat transfer processes. So I'll catch you in the next one.